And based on work kinetic energy theorem, we will discuss another law called the law of conservation of mechanical energy. It follows from this itself. Okay, so understand this carefully. Can any of you tell me the basic formula for kinetic energy of an object?
Half mv square.
Half mv square. Aishwarya, are you aware of this formula?
Yes, sir.
Right. You must have learned in your lower classes also. If an object or a particle of mass m moves with a speed v, then its kinetic energy is calculated as half m v square. Okay. What is the SI unit of energy? This is the first time we are talking about energy, right? And the first kind of energy we are discussing is kinetic energy. Basically, any moving object will have kinetic energy, and it is calculated this way, half mv square. So the formula you learned in your earlier classes is correct only. What will the SI unit of energy be?
Joule.
Joule. Okay. Work and energy have the same SI unit, joule. Fine. And by definition, work is nothing but transfer of energy. So the amount of work you do is same as the amount of energy you transfer. Right? So work and energy should have the same units. Fine. So, right, based on mass and speed, you can tell what is the kinetic energy of an object. That's okay. What is the basic formula for work done by a force? Basic formula for work done by a force. Okay, Aishwarya, what are the factors on which work done by a force depends?
So the force applied and the displacement.
Force and the displacement. Yeah. So are you not able to recollect the formula?
Sir, Fs cos theta.
But that is not the general formula for work. That Fs cos theta is valid only when force is constant.
So force into displacement.
Rishi, you need to be more careful, okay? Had you, like, if you had been in an actual class, I would have made you stand. I told you many times, don't say force into displacement like kids. Okay, there's no into between two vectors. Force is a vector, displacement is a vector. Tell properly.
Force dot displacement.
Yeah, force dot displacement, but that is also valid when the force is constant. Okay, you said F dot S, she said Fs cos theta. It's the same thing. But both are valid only when force is constant. How do you calculate work generally? Pawan, what is the basic or general formula for work? Okay, it is integral F dot ds. Okay, this way you can calculate work done by a constant as well as a variable force. This formula always stands. So this is the basic formula for kinetic energy of an object, half mv square. And the work done by any force is integral F dot ds. And remember, okay, half mv square gives you the kinetic energy only when the entire mass m moves with the same speed. And I told you before also, for this chapter, we are going to consider an entire object moving with the same speed itself. We won't consider different parts of the object moving with different speeds. Okay, we won't consider rotation. So all particles of an object move with the same speed. That means the entire mass of the object moves with the same speed. Then you can use half mv square to calculate its kinetic energy. Next chapter, system of particles and rotational motion, you will learn how to calculate kinetic energy of an object in which different particles move at different speeds also. Okay, all that we'll discuss in next chapter. For now, you can use half mv square, nothing wrong in that. Okay, integral F dot ds gives you the total work done over a certain displacement. If you want the small amount of work done, dW, it is given by F dot ds. Okay. Can one of you tell me the basic formula for dot product? What is the formula for A dot B?
AB cos theta.
AB cos theta, correct. And you can also consider it this way. You can write it as A multiplied with component of B parallel to A. Okay, component of the second vector in the direction of the first vector. We can take it like that also. Now, work done, like if you consider this as the force and this as the displacement, ds. Fine. In like when you evaluate F dot ds, basically what you will be doing is you will be multiplying the tangential force component. Okay, this is F parallel. That's the tangential force. Okay, component of force in the direction of small displacement. So you'll be multiplying the tangential force with the magnitude of displacement. That's what you will be doing. Okay, if you do FDS cos theta also, that is what you get, because F parallel is nothing but F cos theta. So if you are doing F parallel multiplied with ds, effectively you are doing FDS cos theta itself. You are evaluating FDS cos theta itself. Is this point clear to all of you? What F parallel into ds means, how it is same as FDS cos theta? Did you all understand this? Rishi, is it clear?
Yes, sir.
Okay. Now one of you tell me, what does tangential force do to an object? The component of force in the same direction as the motion of the object, what does it do to the object?
It changes the speed of the
Changes the speed, correct. So that component of force which is parallel to displacement can be written as mass multiplied with tangential acceleration. So I'm writing tangential force as mass into tangential acceleration. I'll put a star here. Okay, because there's a condition involved, you'll understand what it is. And multiply that with ds. Okay. Tell me, what is the formula for Newton's second law if mass is constant?
F net is equal to m dot a. M a, sir, M a.
Okay, don't simply put dot everywhere. Mass m is a scalar. Scalar can be multiplied directly with the vector acceleration. Newton's second law, the formula is F net equal to ma. Look at what we have done here in the steps that I have written on the left side. I equated tangential force to mass into tangential acceleration. Now you can't just consider one of the forces and equate it to mass into acceleration. That would be wrong. If multiple forces are acting on an object, you can't just take one force and equate it to mass into acceleration. Okay, it's always net force is mass into acceleration. Rishi, good that you said net force. I'll see some of you joined just now. Let me explain what we are discussing. The class just started. We are discussing something called the work kinetic energy theorem. Okay, one of the most important theorems you will be learning in your syllabus. Okay, why most important? Because it is used in almost every chapter that follows from now. Okay, so first we talked about kinetic energy of an object. Kinetic energy, the like formula that you had learned in earlier classes, half mv square, you can use that directly. And work kinetic energy theorem relates the work done on a system to the change in its kinetic energy. Now we know that doing work is nothing but giving energy or taking energy. Okay, so work kinetic energy theorem proves that the amount of work done is equal to the change in kinetic energy. Okay, anyway, we'll summarize it later also. So we took the basic definition of work. dW is equal to F dot ds. Dot product makes it F parallel into ds. And yeah, this last step, I am equating the tangential force to mass into tangential acceleration. That means I am considering the net force. Okay. So the F here also has to be the net force. And if you are considering work done by the net force, means all forces acting on the particle, that means you are considering total work done. Only then this step would be valid. That's why I put the star here. Okay. Is this clear to all of you? Any doubt in this? If you want to write F as MA, you have to ensure that F is the net force. Okay, so let F be the net force. And if F is the net force and you are calculating work done by the net force, that means you are calculating the total work done on the particle, a single particle. Okay. What is ds in the formula for work done? What does it mean?
Small displacement.
Small displacement. Okay, so small you can't even tell how much it is. In such a small displacement, will distance be equal to magnitude of displacement or not? If direction does not change. See, ds is so small a displacement, direction change is not possible during that interval. If direction change is not possible, can we say distance is equal to magnitude of displacement or not? Something we learned in motion in a straight line.
Yes, sir, we can.
We can, okay? In fact, only when direction of motion does not change, distance will be equal to magnitude of displacement. So we can do that. So in the formula for work, ds bar is displacement. Okay. And here ds is magnitude of displacement. And because it's so small that direction change is not even possible, you can call it as distance also, nothing wrong in that. Small distance moved by the object. Okay, it's reasonable. I mean, it's valid, nothing wrong in that. Fine. So what do we have here? dw, the small amount of work done on a particle during a small displacement, is m, the mass of that particle, at, tangential acceleration of that particle, multiplied with ds, the small distance moved by the particle. Okay. We know that tangential acceleration by definition is rate of change of speed with respect to time. We had discussed this when we talked about when we discussed circular motion. Okay, in laws of motion. We even wrote equations of kinematics with tangential acceleration, distance, and speed. Okay, so by definition, tangential acceleration is rate of change of speed. And speed is rate of change of distance covered with respect to time. These are just definitions. Divide these two equations. Rishi, tell me, when you divide these two equations, what will you have on the left-hand side? Just what terms will be there on the left-hand side? No response. Okay, Pawan, you tell me, what terms will you have on the left-hand side?
Sir, AT by V.
AT divided by V is equal to, what terms will you have on the right-hand side?
dV by ds.
dV by ds. The dt will get cancelled. Correct. So AT by V is equal to dV by ds. That means AT multiplied with the distance ds can be written as V dV. In fact, we discussed this in motion in a straight line also long back. We know A is equal to V dV by dx. We used to write this. Okay. And from this itself, by integrating, you get V square minus U square is 2as when acceleration is constant. Okay. So the same relation here, nothing new. Just showing you that AT into ds can be written as V dV. We will substitute this AT into ds is V dV over here. in the work done. Why? Because we want to relate work to kinetic energy of an object. Kinetic energy depends on speed of the object. So you should somehow get speed into this equation. That's why we are doing all this. Okay. So dW can now be written as, it was earlier MAT, that is the net force, net tangential force, and the small distance. We will now write this as MV dV. Okay. dW is MV dV. dW is a small amount of work done. Integrate that, you will get the total work done. Integral dW simply becomes total work done W. You can write delta W also, nothing wrong in that. But total work done becomes equal to M. The mass of a single particle is constant. We'll put it outside. Integral V dV, this is its speed. You have to integrate its speed. And you will integrate it from initial speed to final speed. Can one of you tell me what is integral V dV? Or integral X dx?
V square by
V square by V.
V square by 2. Okay. And limits U to V if you take. M by 2 can be kept outside the bracket. And inside you will be left with V square minus U square. This is the proof. First term is half M V square minus second term is half M U square. Half M V square is the formula for what?
Kinetic energy, sir.
Kinetic energy, and V stands for final speed of the object in the interval that we are interested in. So this becomes the final kinetic energy of the particle. Minus U stands for initial speed. So this becomes initial kinetic energy of the particle. Okay. The particle undergoes a certain displacement, no? At the beginning of the displacement, it would have had some speed. It could be 0 also. At the end of the displacement, it will have some speed, maybe even 0. Okay. So those are the terms that we see here. Final speed, initial speed. Half mv square is final kinetic energy. Half mu square is initial kinetic energy. And what do you have on the left-hand side? Work done by the net force. That means work done by all forces together. And this is what is work kinetic energy theorem. We can write the statement like this. The total work done by, okay, all of you write the statement, this is very useful. Total work done by all the forces acting on a system. When we say all the forces, we include internal and external forces. And the total work done by all forces is equal to the change in the kinetic energy of the system. And this theorem is particularly useful, is extra useful compared to other theorems and laws, because this does not come with any condition. This is always valid. See, in laws of motion, we discuss something called law of conservation of linear momentum. Can one of you quickly recollect and tell me, when is linear momentum conserved? Or what condition do you check before applying conservation of linear momentum?
F net equal to 0, sir.
Net force has to be 0. So it comes with a condition. Linear momentum of a system is not always blindly conserved. Okay. But this is one theorem or one formula that you can always use. But you have to ensure that you are including total work done by all forces. You can't take only some of the forces. Okay. Total work done by all forces acting on a system is equal to the change in kinetic energy. That is what is work kinetic energy theorem. And this is proof that the way we defined work, okay, we defined work as F dot ds, right? Mathematical formula for work is F dot ds or integral F dot ds. So this is proof that integral f dot ds does indeed give you the kinetic energy given to a system or taken away from a system. Okay, let's go through the proof once again. In NCERT textbook, I think you will find the proof assuming force is constant. I think they'll use equations of kinematics for proving that, but you don't even have to consider that condition. The force can be variable also. The multiple forces acting on an object can all be variable. Still, this theorem is valid. Okay, so let's go through the proof once again, and then today's class will all be about application of this theorem. So basic formula for work done, W is integral f dot ds. That's the work done in an entire displacement. But in a small displacement ds, you can write dw is f dot ds. Okay. F dot ds from the basic definition of dot product becomes f ds cos theta. F ds cos theta is nothing but the parallel force F cos theta multiplied with ds. Okay. Or the tangential force F cos theta multiplied with the magnitude of displacement ds. So I wrote F parallel into ds. So nothing new. This is all known already. F parallel is the tangential force acting on the particle. ds is the magnitude of displacement. And if you consider the net tangential, just a moment, it got disconnected for some reason. Are you all able to see my screen?
Yes, sir.
Okay. So if you are considering the net tangential force, you can equate it to mass into tangential acceleration. That's from Newton's second law. And since the displacement is very small, magnitude of displacement can be taken as distance also. So we get dw, small amount of work done in a small displacement, is m at, tangential acceleration, ds, distance. And then we proved that from definition of tangential acceleration and speed, we proved that at ds can be written as v dv, where v is the speed of the object. And then we rewrite that equation dw is equal to m at ds as mv dv. After that, it's simple integration substituting limits. So we can conclude that total work done by all the forces acting on a system is equal to the change in kinetic energy of the system. Okay, any doubt in the proof? Anyone? And since we use the integral method, the proof is true in general. The force doesn't have to be constant. We didn't use equations of kinematics anywhere in the proof. Fine. So acceleration need not be constant. That means the force need not be constant. So work energy theorem is applicable to work done by variable forces also. Okay. Now, how are you going to use this in solving problems, while solving problems? Let's write the mathematical form first. Total work done, delta W, or simply W also you can, let's use W only for convenience. Total work done by all forces is the change in kinetic energy of the system. For now, we'll be interested in one block only. After that, we'll include multiple blocks also in the next chapter and all. So we can write this as half m v square minus half m u square. So we have a formula here involving some terms, right? And using this formula, except one term, if the others are given, you can find out the unknown term. So they may ask you to calculate work done. You can use work energy theorem in calculating work. They may ask you to calculate the final speed of an object. After reaching somewhere, what will its speed be? That can be done using this theorem if the other terms are given. Okay, if we know the other values, then we can find this out. You may even be asked to find out the initial speed of a particle or an object. You can use it for that also. But to find out initial speed, you need to know the final speed and the work. Okay. And see, work here is the total work done. You have to include work done by all forces. So you can use work kinetic energy theorem to calculate work done by force, to calculate final speed, or to calculate initial speed, provided the other values are given or the other values can be derived. Okay, let's go back to one of the problems we had solved before. Maybe this constant force case. Just a moment. Okay, yeah, this one. A block sliding down a rough incline. We know there are multiple forces acting on it: weight, normal force, and friction. We had calculated work done by weight. We found out that it is 240 joules. It is highlighted there. We saw that normal force doesn't do any work in this case. Can one of you quickly tell me why work done by normal force in this case is 0? As the block slides down the incline, why is work done by normal force in this case 0?
Angle between displacement and normal is 90 degrees.
Angle between the force normal and displacement is 90 degrees. Their dot product becomes 0. That's why the work done by normal force is 0. And we calculated how much friction acts on it. Friction, displacement, they are in opposite direction. And we found that friction does a work of minus 160 joules. So we found out work done by all forces on this block. Okay, one of them did plus 240 joules, the other one did 0, the third one did minus 160 joules. So let's kind of continue this problem. Tell me, how much is the total work done by all forces then on this block? One did 240, the other did 0, the third one did minus 160. What is the total work done? Two forty, 0, minus 160. What is the total?
80, sir.
80 joules of work is done. Okay. Let's verify, since we have considered work done by all forces, let's verify if this is equal to change in kinetic energy of the block or not. Okay. Now this block, assume it started from rest. So initial velocity, let's take it as 0. We have to calculate the final velocity so that we can find out the change in kinetic energy and verify work energy theorem, whether it is valid in this case or not. Now we know the displacement, the slant displacement is 20 meters. Initial velocity is 0. U is known, S is known. What we want to find out is V, the final speed. Tell me which equation can be used to do this. Which equation can be used to derive the final velocity of the block as it reaches the bottom of the incline?
V square minus U square equal to 2S.
Correct. If acceleration is constant, we can use V square minus U square is 2S. Now the three forces acting on this block are constant only. Weight won't change. Friction, kinetic friction, that won't change. Why? Because the slope is uniform, no? Friction is always mu n. N is mg cos theta. Theta is not changing. Normal force won't change. Friction won't change. All forces are constant. Acceleration will be constant. Okay. Can one of you tell me, just look at the diagram and tell me, how much is the net force pulling the block down? Because from net force only we can get acceleration, and using that in equations of kinematics, we can tell the final velocity. How much is the net force pulling the block down? All magnitudes are written on the screen. Just see and tell.
4 Newton, sir.
4 Newton. How did you arrive at that answer?
Friction, sir.
Okay, some of your statement got cut. Anyway, mg sin theta minus friction. Mg sin theta is 12 newtons, friction is 8 newton. So the net force is 4 newton. Okay, net force is 4 newton, mass is 2 kg. Rishi, tell me, how much will the acceleration of this block be?
So, can you repeat what you just said?
Net force is 4 newton. The mass of the block is 2 kg. How much will its acceleration be? Okay, anyone? How much will the acceleration of the block be?
meter per second,
At
sir.
2 meter per second square. Net force divided by mass, 4 divided by 2. So initial velocity is 0, displacement 20 meters, acceleration 2 meter per second square. We need final velocity. We can use equations of kinematics. V square minus U square is 2AS. So you get V square as 2 into 2 into 2 is 880. Let it be. Initial velocity was 0. U square is 0. V square is 80. Now we want to check whether the total work done is equal to the change in kinetic energy of the block or not. We got total work done by using definition of work and all we got. Now we will calculate change in kinetic energy. And how is that done? Half m final V square minus initial U square. And that's half into mass here is 2 kg. V square is 80. U square is 0. These two cancel. And you see that change in kinetic energy is 80 joules, which is equal to the work done by all forces combined. Work done by individual forces is not 80. Weight did not do 80 joules of work. Normal force didn't do 80 joules. Friction didn't do 80 joules. But combine all of them, the total work done was 80. And we see that that is equal to the change in kinetic energy of the block. Okay, so we just verified work kinetic energy theorem in one of the problems that we had already solved. Okay, let's apply work energy theorem now in some questions. Fine. An object of mass, let's say 7 kg, one direct question, moving initially at a speed of say 10 meters per second is later found to move at say 6 meters per second. Calculate total work done on this object. Type your answers in chat and I want all of you to solve quickly. The question is about total work and you can see there's no force given to you in the question. Okay, without giving a force, they're asking you what is the total work done, but they have given you in the question the initial speed of the block and the final speed of the block or object, whatever it is, and the mass. So now you have to think like we have learned a new way of calculating work based on the mass and speeds. You have to apply that. I got answers only from 3 of you. This is a straightforward, direct question. Yusuf, can you unmute?
Yes, sir. Yes, sir.
Yeah, how are you trying to solve this? You are asked to calculate total work done and you are given mass and initial final velocities. How are they related? Rishi, check your calculation. Your answer is not correct. Okay. Rishi, how did you calculate?
Sir, half mv square minus half mu square.
Half mu square minus half mu square. Do that directly. Half m is 7. How
Yeah,
much is
sir.
v
And
square?
v square is 36.
Minus u square?
U square is 100.
100. How did the answer become positive then?
Oh yeah, I forgot to put the
Yeah, you forgot the minus. That's fine, but it's it will be a costly mistake if you do that in your final exam. So the answer is, I think you all gave magnitude as 224. So minus 224 joules. Okay, good. So this is a direct application of work energy theorem, work kinetic energy theorem. So look at what happened in this problem. We calculated work done without knowing any force, but we calculated total work done by all forces. Now, who knows how many forces are acting on this object? Okay. And for the answer, it doesn't matter also. You are asked total work done, not work done by a particular force. So in such cases, you can make use of work energy theorem also. Let's try one more case. Last class, we considered we considered some variable forces and calculated work done by them. Like one problem was this, 2x I cap. So here force varies based on the position of the object. So it's kind of force in terms of displacement given to you. Okay, force in terms of position or force in terms of displacement is given to you. Even in the question that followed, the coefficient of friction varied with the position. So you indirectly knew friction in terms of position. So force displacement equation you already knew. So these two questions, the variable force questions that we discussed in the last class, both involved forces as functions of displacement, okay, or position. Position, I should say, not displacement. Both involved force as a function of position, but not time. Suppose you are given something like this. An object of mass, let's say 5 kg, moving with a velocity, let's say 10 I cap meters per second, is acted upon by a force. Okay, only one force is acting on it. F is equal to 4 I cap, okay, variable force, 4 T square I cap newtons. So the mass is given, the initial velocity is given, and the force acting on the object is given. Since there's only one force, that itself is the net force. The question is to calculate work done by this force from t is equal to 0 to, let's take 2 seconds. So in the first 2 seconds, 0 to 2 seconds, how much work does this force do is the question. Think carefully and try to solve. Okay, listen, all of you. I didn't get any answers. But observe the question. You are given a force which depends on time. So you don't know how the force varies with displacement or position, but time to time you know how it varies. That's one thing. And you are asked to calculate work done. Fine. I got one answer as 175 joules. We'll see. I don't know if it is correct. But Pawan, you only tell me, what are the different methods you know to calculate work?
సార్ ఫస్ట్ నేను యాక్సిలేషన్ కనుక్కొని దాన్ని S = UT + half display పెట్టాను సార్.
See, I asked you what are the different methods you know to calculate work.
Integration of FDS
Huh.
into difference of kinetic energy.
Okay. See, here there's only one force acting on this object. So the work done by this force itself becomes the total work. Okay. So we can use both methods to solve this problem. You can use W is equal to integral F dot ds. You can also use work is equal to change in kinetic energy. So like today you learned a new method to calculate work. Fine. But that new method only helps you calculate total work by all forces. You can't find out work done by individual forces directly using the work energy theorem. Indirectly you can. We'll solve problems, you'll understand. Directly you can't. But here, since only one force is acting, work done by that force itself is the total force. Work done by that force itself is the total work. So any of these can be used. Now, we know this force is a variable force. By looking at the equation itself, you can tell time to time it's going to change. Means from place to place also it will change, obviously. So this is a variable force. So if you want to use integral F dot ds, can you simply write force is 4t square, displacement ds, and can you say integral of t square is t cube by 3. So can you say this is 4t cube by 3? Tell me, is this step valid or not? Any one of you?
No, sir.
Okay, Vanilla, why is this not valid?
Sir, because you have to integrate with respect to ds.
Correct. The force varies with respect to time. Okay. But the integral is with respect to displacement. You can't directly integrate like this. Had it been dt, then you could have written 4t cube by 3. But with ds, you can't. So directly we cannot proceed this way to calculate the work done. Because we'll get stuck here, we won't be able to integrate this. So if you still want to use this formula, W is integral F dot ds. If you want to use this, you should first express force in terms of displacement and then substitute. Okay. And I think that is what Pawan has done. Pawan, now tell me the exact steps that you have taken.
Sir, same sir. దాని తర్వాత S = UT + half square లో పెట్టాను సార్.
Okay. From force, you found out acceleration.
Yeah, sir.
Mass is given as 5 kg. Force is 4t square. Let us solve it using this procedure first. Since that is the only force acting on the object, that itself will be the net force. So F is equal to 4t square is equal to mass into acceleration. And from there, he got the acceleration. 4 by 5 is 0.8. You can write it as 4 by 5 also, nothing wrong in that or nothing harmful in that. 0.8 t square is the acceleration. Pawan, what did you do after this?
Sir, దీని తర్వాత S = UT + half square లో పెట్టాను సార్.
Why will you put this in S is equal to ut plus half a t square, sir? Is this constant?
అలా కాదు సార్, నేను చెప్పేదంటే ఏలో పెట్టి ds/dt చేద్దామని. దాని నుంచి ds కనుక్కొని
No,
అప్పుడు ds plus
wait. You want to use this acceleration in S is equal to ut plus half a t square.
Yeah, sir.
How? Tell me the exact equation that you will write. S is equal to U is how
UT
much?
+ half t square.
U and then 10 into t plus half. What will you put in place of a? Just A.
0.8 into t square.
How can you put variable acceleration in this equation? That is what I'm asking. A itself is 0.8 t square. Another t square also you will have. Okay, this step is invalid. You can't find out total displacement using this. Okay. Can any of you tell me how to proceed from here? I don't want you to use the other method. Other method we'll discuss. But if you want to solve this problem this way itself, using the basic formula for work, how to take the next step? Okay, listen carefully. If any of you wants to tell quickly.
So we can write acceleration like dv by dt.
Okay, correct. You can write. That's the only thing you can do. If acceleration is variable in terms of time, you write dv by dt. Okay. Then the next step would be dv is equal to 0.8 t square dt. Integrate both sides. Integrating dv becomes delta v, means final velocity minus initial velocity. Initial velocity is 10 I cap. So I'm writing it as 10 is equal to 0.8. T square integral is t cube by 3. Okay, if you do this, you will get final velocity is 10 plus 0.8 by 3 into t cube. Vanilla, what will you do next?
So we can substitute t as 2 seconds.
If you substitute t as 2, you will get final velocity. And then what will you do? What will you do with final velocity? Okay. See, one thing that can be done is use that final velocity in work energy theorem. So you'll jump to the second method. Otherwise, if you want to struggle with the first method, you can do like this also. You equate velocity. By definition, velocity is displacement by time, no? Or rate of change of position with respect to time. ds by dt you can write, or dr by dt, whatever you are comfortable with. Then you will get small displacement is equal to 10 plus 0.8 by 3 t cube whole thing into dt. Now you are in a position to solve the problem. Using this method itself, what you need is integral f ds. Okay, f dot ds, that is f ds cos theta. Now, force was 40 square. 40 or 40 square? 40 square. In place of ds, you can now write this big expression. 10 plus 0.8 by 3 t cube dt. Now you see that everything is in terms of time. And you integrate this with the limits of time given to you in the problem 0 to 2, you will get the work. Okay. But look at how many steps we did. If you want to do it this way. So not necessary. Fine. You don't have to write force in terms of displacement every time and then calculate work. We have learned another method today. We'll try to apply that. Okay. W is equal to delta K, change in kinetic energy. Let's try to do this. We know the mass and initial speed. So we know the initial kinetic energy. All we need is the final kinetic energy. And what we have here is force as a function of time. F is equal to 4t square. See, I cap is fine. Force is in the positive x direction. Object is also moving in the positive x direction. Everything will be positive. So let's leave I cap for now. This is the force magnitude, 4t square. We know mass. We know initial velocity. We know the force. How to get final velocity? Can one of you tell me how these are all related? I think some of you will say, sir, it's part of what we did in the last method. Get acceleration from force, and from acceleration, get the final velocity. That's what Vanilla said. Okay, that's one way to do. Can be done. There's another way also. Without finding acceleration also, you can proceed. We know force is, net force is rate of change of linear momentum. Newton's second law. So dp is f dt. Integral dp is integral f dt. Integral dp becomes the total change in momentum is integral f dt. Okay, since direction is all positive x, I'm not writing it. Total change in momentum becomes mass into final velocity minus initial velocity is integral force is 4t square dt from 0 to 2 seconds. From this, you can directly tell the final velocity. Okay, so integrating force can give you final velocity. Of course, see, if you look at the solution for the first time like this, it may feel like there are a lot of steps here also, but once you get used to it, you will directly write this step. Okay, change in momentum is integral of force with respect to time. If you do that, you can tell the final velocity. You will get the final velocity. Now, mass of this object was 5 kg. Final velocity is unknown. Initial velocity is 10. Integral 4t square is 4t cube by 3. So 4 by 3 into t cube. Substitute limits 0 to 2. 2 cube is 8. 4 into 8 is 32 by 3 is the right hand side. Send the 5 to that side. You get v minus 10 is 32 by 3 into 5 is 15. From there, you find out final speed. Once you know final speed, you do work is equal to change in kinetic energy. Okay. So at like when you look at these solutions, it may appear like both solutions are equally lengthy. But once you get used to it, used to what? Whenever you see force as a function of time, no, you must get the thought in your mind that force can be related to momentum through Newton's second law. Okay, so whenever force is given as a function of time, mentally you think of it as dp by dt. If you are sure that this is the net force. Okay, and from momentum you will get the final velocity. You can proceed that way also. So it kind of appears like a tough question, but once you know this idea, the next question you can solve easily. Is the solution clear to all of you? Both methods. First method was from force we find acceleration. From acceleration we get velocity, final velocity. Go to work energy theorem, use that. Otherwise, from velocity get displacement, use in the formula for work itself without using work energy theorem. The second method is direct use of work energy theorem, but we don't know the final velocity. To get final velocity or final speed, we related force to momentum. Okay, force, momentum, and time are related as F is dp by dt. If you are sure that F is the net force, from that you get final velocity. Apply in work energy theorem equation, you will get the total work done. Is this clear to all of you? Any doubt in this? Okay, solve this question. Object of mass 4 kg, initially at rest, subjected to a force of, let's say, 40 cube newtons. Calculate work done in 10 seconds. Solve this quickly. Type your answers in chat. Okay, I got one answer as 1, 2, 3, 4, 5. So 1 crore 25 lakhs. So you can write 125 into 10 power 5 joules. We'll see. Solve it quickly, all of you. 1 more minute. Okay, let's see. Rishi, let's discuss. You gave an answer. So how did you solve?
Sir, first m into v minus u is equal to
Hmm.
4t cube dt with limit 0 to 10.
Wait. M into V minus U is change in momentum. Okay, so you are using delta P is integral f dt. Okay,
Yeah,
so
sir.
wait. M into V minus U is, okay, this first step is correct only. 4t cube dt with limit 0 to 10. Yeah. And substitute mass is 4 kg, final velocity is unknown. So left hand side becomes 4v because U is 0.
Is equal to 40,000.
You will get 4 into t power 4 by 4. That 4 will get cancelled. It won't be 40,000. It will be 10,000. Okay.
Yeah, sir. 4v is equal to 40,000, v is equal to 10,000.
4v itself is 10,000.
Oh,
See,
one
the
second.
integral becomes t power 4 by 4. The 4 that is already there beside t cube and the by 4 will get cancelled. So this becomes
Yes. My
10,000. So you get V as 10,000 by 4 is 2,500. And then you calculate change in kinetic energy. That itself will be the work done. So the answer is half mass is 4 kg into V square to 2500 squared. 25 squared is 625. 100 squared is 10 power 4. So half mv square minus u square. U square is 0. You don't even have to write that. That is the answer. Okay. So 625 into 2 is 1250 into 10 power 4 joules. Or you can write 1.25 into 10 power 7 joules. Okay, check this once again, all of you, and ask me if you have any questions. since you are given force in terms of time, you first relate it to momentum, get the final velocity, then substitute it in work energy theorem. Is it clear, Pawan? Did you understand?
Yes, sir.
Why were you not able to solve? And where did you get stuck?
Sir, calculation MD వచ్చింది ఇక్కడ కాదు.
Okay. Aishwarya, why were you not able to give an answer?
Sir, I was unable to access the chat, sir.
Oh. Okay, no problem. Yusuf, where did you get stuck?
So formula.
Formula. Okay, now is the idea clear?
Yes.
Okay. Next question. Consider a rough inclined surface with a block on it. Let's say the angle of inclination is 37 degrees. Assume this height is 20 meters. Mass of the block, let's say, is 5 kg. Block is released from rest. It is found that the block reaches the bottom of the incline with a speed of 10 meters per second. Calculate work done by friction during this displacement. Okay, think carefully and solve, all of you. Is all the information given? Yeah. I got only one answer so far, that 2 minus, okay, minus 750. And negative makes sense. We'll see. Pawan, how are you trying to solve?
Sir, first distance కనుక్కుని దాని తర్వాత force కనుక్కున్నాను.
Where will you find the force from? How will you find out friction?
Friction సార్ నేను చెప్పేది ఫస్ట్ అంటే ఎంతవరకు స్లైడ్ అవుతుందని ఫస్ట్ డిస్టెన్స్ కనుక్కున్నాను.
Okay, you will get that slant distance. And then?
దాని నుంచి యాక్సలరేషన్ కనుక్కున్నాను.
Okay, so he's saying using trigonometry, we'll find out the distance first. Distance, displacement, same thing. From that, we'll find out the acceleration. And then
నెట్ ఫోర్స్ కనుక్కున్నాను.
from acceleration, he'll find out net force. And then
దాని తర్వాత ఆలోచిస్తుంది.
okay, you can proceed that way. From net force, you can find out frictional force. And then you can find out work done only by friction. Can be done. Vanilla, how did you solve? You gave an answer. Is that the same method you used?
No, sir.
How did you solve?
So work done by gravity minus work done by friction equal to change in kinetic energy.
Okay, you used work kinetic energy theorem. See, there are two ways to calculate work now. You can use f dot ds or integral f dot ds, that can be used, or work done by all forces is equal to change in kinetic energy. Now in this problem, there are multiple forces acting on the block. You know normal force will act. You know weight will act. Okay, I'm showing weight as it is without the components. And you know friction also will act. There are multiple forces acting and there are multiple forces that do work also. Can one of you quickly tell me, out of these three forces, which are the ones which do work as the block slides down? Which are the...
mg sin theta and frictions.
Okay, you can say mg, weight does work and friction does work. Normal force is perpendicular to displacement. So work done by normal will become 0, but friction will do, weight will do. So you can write an equation like this: work done by weight plus, Vanilla, you said minus, that is wrong, plus work done by friction. One of them, like work done by friction, can be negative. You can't put the minus sign in work energy theorem. Okay, sum of work done by all forces is the total work. Okay, plus work done by normal force is equal to change in kinetic energy. And in this problem, you are given the final speed, initial speed, mass. So you know the change in kinetic energy. You know work done by normal, it is 0. You need work done by friction. If you can somehow find out work done by weight, then directly you can tell work done by friction. Without calculating friction itself, you can tell. Okay, let us proceed this way. So we need to find out work done by weight during this displacement. One of you tell me, is the weight of the block a constant force or a variable force?
Constant, sir.
Constant. And how do you find out work done by constant forces? What is the formula we use to calculate work done by a constant force?
Fs cos theta.
F dot S, Fs cos theta. Correct. Now the work whose, the force whose work we want to find out is weight. Okay, weight of the block. Block's mass is 5 kg. So its weight is 50 Newton. We don't know the total displacement of the block. Okay, we have not calculated, but we need component of displacement in the direction of force only, no? This angle will be theta. S cos theta is nothing but this displacement, which is directly given to you, 20 meters. So you don't have to take the total displacement and take cos theta again. Directly use 20, because 20 is the displacement in the direction of the force mg. So you already know force and displacement in the same direction. Okay, you can use it. So F is 50. S cos theta together becomes 20. So work done by weight 50/20 is 1000 joules. Okay, we can do it the way you said also. You are saying mg sin theta will do work. Based on that you calculate it. You can do it that way, but unnecessary. You can tell work done by weight directly. So weight is doing 1000 joules of work. Let it do. Now work done by normal force we know is 0. Work done by weight we found out is 1000. Next, change in kinetic energy, half into how much was the mass? 5 kg, into with what speed is it reaching the bottom? 10. V square minus, initially it was at rest, U square. That's all. Therefore, work done by friction becomes, how much is the right hand side? 10 square is 100. 100 into 5 is 500 by 2 is 250. Minus weight did a work of 1000 joules. So friction does a work of minus 750 joules. This is much easier than calculating displacement, with that calculating acceleration by using equations of kinematics, from that finding out net force, from that finding out frictional force, then finding out work done by friction. Pawan, do you think this is much easier or not?
Yes, sir, it's easier.
Okay, so see, the takeaway from today's class would be that you learned another method to calculate work. Okay, not just using force and displacement. There are other techniques to calculate work, and we are solving problems based on it. Did you all understand the method that I used? Any doubt in this?
Sir, so you added up all the forces acting on the block and then
I added up
equated it to.
work done by all the forces. Yes.
Okay, sir. Okay.
One of the forces was not doing any work. The other forces work done was easy to calculate. Work done by weight is easy to calculate. I use this method. Okay, hope this is clear to all of you. We'll stop it here for today. Tomorrow you'll get a worksheet based on work energy theorem. Like, see, you have to decide which method to use. Whether you'll use the original method integral f dot ds, or you'll use this new method work energy theorem to find out the work done in a particular situation. Okay. And I'm telling you again, the theorem is very, very important. We'll be using this in almost every chapter that follows. And this will have more applicability because this theorem doesn't come with any condition. You just have to ensure you have taken work done by all forces, equated to change in kinetic energy. In any problem, you can apply this. Okay, where appropriate questions are asked, you can apply. Okay, fine. We'll continue on Wednesday. Tomorrow you will be given a worksheet, solve those questions.
Thank you, sir.